Hi, I'm Martha, an overworked engineer.
I'm Flip.
And be it here.
And Mel here, the world's worst boss? I don't know anything. Martha, I have a little project for you.
Hey, it's Raheem's turn to feed the salamanders.
So, our VP heard about machine learning and wants us to add it to everything. Can you lead that effort?
Machine learning? That's not exactly my area of expertise.
Okay, good luck. Gotta hop on a call. Thanks, bye.
But... Oh no, is there even anyone here with machine learning experience? Gotta be someone...
At this place?
Great. 10 more white papers. Here I come. Wait, what? Hello? Is somebody there?
Sorry about that.
Somebody forgot that humans can't see in the dark.
Okay, did I just hit my head or something?
No, this is actually happening. Our model predicted you'd need some machine learning answers about now. I'm Bit, by the way.
And I'm Flip. Tell us, what do you think ML is? Tragically underspec human.
Name's Martha. Machine learning is a subfield of artificial intelligence, right? Along with image recognition, language processing, recommenders, self-driving cars, and, time traveling, Schwarzeneggers, taunting Keanu Reeves?
You got the first part right.
Machine learning can be seen as a subfield of AI, but it's also an essential part of all those other fields. Machine learning is when computers improve at a task based on experience at that task, but without explicit programming.
In other words, computers finally starting to take the initiative in ways they rarely have before. Arthur Samuel at IBM coined the term machine learning way back in 1959, just a few years after Alan Turing started talking artificial intelligence.
Hold on. If machine learning has been around that long, why is it such a buzzword now?
New engineering insights, well-curated big data sets, and hardware that can keep pace have all converged to make today's ML shine.
And by shine, he means it can produce useful results before the heat death of the universe.
That's cool and all, but without explicit programming sounds fishy. I mean, it's all in the code somewhere. How is ML different from the way I program now?
ML is powered by data, not instructions. We'll show you. Hey, Bit, ML metaphor mode.
Sure thing.
Where were you hiding that?
Let's try some classification. We can start with this fork. Okay, buddy. This right here, this is a fork. Got it? Now, what is this?
Based on what you've told me, I'm 100% confident that this is a fork.
Yeah, I'm not impressed.
Sorry, amigo, it's not a fork.
Oh, gotcha. Not a fork.
Now, what's this?
I'm 80% certain that's a fork.
Perfect, but that's easy. I can do that without ML and with 100% accuracy. Okay, guys, stop joking. I can easily write a program like this.
Okay, fair enough. But now do that for every type of fork in the world. Plastic forks, antique forks, two-tined forks, five-tined forks, giant forks, glass forks.
No. I'd have to write out all the possible characteristics that make something a fork to define forkiness itself.
Exactly. But with ML, if you have enough well-curated data and run it through enough training and testing, can you guess what this is, buddy?
I'm 93.4% sure that's a fork.
Okay, I'm starting to see your point.
Obviously, there's a lot more to it in real life, and ML covers more than just classification.
But on the whole, ML's data-centric approach makes it great at learning by example, finding patterns in data, and predicting outcomes.
Sounds great, but how can a machine learn exactly?
So let's say you want to predict the prices of houses in Portland, Oregon.
Hold on, does it have to be Portland? These examples are always in Portland.
Aren't all houses in Portland?
Back!
Now let's say you know just the size and price of only 10 houses. How could you use that data set to guess the price of others?
I guess I'd pop them into a spreadsheet and then plot X and Y coordinates and a trend line like in high school algebra.
Exactly, just linear regression, nothing fancy.
Now add 10 more houses.
Oh. Let me just adjust that angle a bit. There, much better.
Aha.
Look what you did there. You used the data to form a hypothesis. New data exposed the errors in your hypothesis. You intuitively measured that error gap, then adjusted your hypothesis to fit.
Humans can learn. It's a miracle.
Oh, cut it out, you dorks. I just saw what was wrong and fixed it, like anyone would.
Anyone, maybe, but not anything. We machines can't rely on intuition to tell forks from spoons or predict housing costs in the only city with houses.
Reducing errors in ML is a journey to be taken one step at a time. Whether for classification or regression problems, ML typically starts with a hypothesis, and of course, some hypotheses will prove more wrong than others.
As ML adjusts hypotheses, that error rate will go up, down, or stay the same. And if you're like most engineers...
Guys, can we go down now?
Exactly.
You want to get down to where the model's error rate is at its lowest, so that you...
No, I mean, I literally want to climb down to... why can't I see anything anymore?
Heh.
You didn't think we'd make it that easy, did ya?
But that error landscape? Where did it all go?
Oh, it's still here, all around us.
But the shape of that landscape, that array of peaks and valleys we call an error function or loss function, can only be revealed by gradually descending through it. It's a journey we call gradient descent.
At every point, the model gauges the angle of steepest descent, much like this elegant antique spirit level used by 4 centuries of carpenters to...
Oh, hey, my phone has an app that does that.
Or, okay, that works too, an app.
Wait for me. So, gradient descent is kind of like hiking down the slopes of wrong into the valley of right?
Yup, or at least into the valley of right enough. Machine learning is part data science and statistics. There's a strong probabilistic streak to it. Think descending equals to solving, plain and simple. Gradient descent is the learning process. enacted in space. Machine learning is a young field. We're all learning as we go, and there are plenty of ongoing challenges, like not getting trapped into a false bottom, aka local minima, during descent.
Heads up! Mel is a moving target. The tools and techniques that seem entrenched today might look very different in the next wave.
So true, buddy. For example, we'll always want to minimize error, but gradient descent may not always be our method of choice. There are other optimizers, as we call them.
Speaking of which, sorry to bring us crashing back to Earth, but do I seriously need some freaky, calculus-filled energy landscape just to price 20 dumb houses with one feature each?
Nah.
No way!
But what if there are 20 million houses with 200 features each?
Yow! Okay, very impressive, but I gotta say, some of these features you've thrown in are a lot less important than others. I mean, size of garden genomes? Come on!
Aha, so are you saying some features should carry less weight than others?
Sure, Oh, they all have knobs now! Perfect! Let's turn that feature down, and turn that one up and... Gang? Is it my imagination? Or are these knobs starting to turn themselves?
Seems so.
Looks like our algorithm is starting to find its own way down the slopes of wrong.
And into the valley of right enough.
Whoa!
In ML, hypotheses flow forward, tuning parameters based on available data.
Dude, you're like this wrong.
Then that knowledge is propagated back through the system to help retune those parameters.
Ooh, getting closer.
That iterative back and forth is the rhythm of most machine learning.
The learning part is that backflow retuning, known as backpropagation here in the era of neural networks.
And though we perfectly understand how backpropagation tunes those parameters,
the resultant settings for some of today's complex datasets aren't so easy to untangle afterward.
Fair enough, I guess. I can barely untangle what's going on in this machine half the time.
hey, at least something is going on in there.
Yeah, that is more than we can say for some humans at your company.
Ah, thanks! So is machine learning mostly classification and regression like in our fork and house examples?
Yes and no, those are useful ingredients in many machine learning recipes.
But at the end of the day, it's your choice of learning method that counts the most.
And these days, there are three methods most commonly used in machine learning tasks.
Which you choose depends on what you want out of your data.
In supervised learning, you use labeled examples of what you're looking for, the so-called right answer, to compare your work against.
Aha, so most of the cases we have discussed?
Are examples of supervised learning. Yes, it's the dominant group, for now.
In supervised learning, the ML model trains on sets of labeled training data, then guesses at the labels of subsequent testing datasets, often in multiple iterations.
Until it's ready to deploy on that final dataset called the world.
Ha ha, so that's what a hedgehog looks like.
In unsupervised, there is no right answer per se. You're on the lookout for clusters or anomalies that may turn out to be meaningful. Such as people who like the same type of movies.
Oh my god, I love that one. So good.
Have you seen that one, though?
ML is a great fit for this kind of work because it can take on a huge or hugely complex dataset.
And in reinforcement learning, the program tries to find the most efficient pathway to its goal. Successful routes get a reward.
Failure's a restart.
One deep reinforcement learning system was so good as classic arcade games, it could switch to a game it hadn't played before, and learn to win with no additional programming.
Whoa, that's bananas!
Yay.
These categories don't account for all of machine learning, but they cover a lot of ground.
So self-playing arcade games are cool and all, but I want to hear more about practical applications. What can this stuff be used for in the real world?
Supervised learning is used in image classification, speech and text recognition, medical diagnostics, and fraud detection, to name a few.
Unsupervised can help us visualize networks, make personal connections, or find patterns in nature. And reinforcement learning could be applied to everything from traffic management to market analysis to robot navigation that won't look OMG so wrong on YouTube.
But no matter the kind of ML, good data is where it all begins. Say you're using supervised learning to identify photos of, I don't know, cats. First, you have to gather data that contain the information you're looking for.
So I'd need to think about dimensions, resolution, aspect ratio, close-ups versus long shots. From what angles? Isolated or in an environment? Are kittens included? Tigers?
Exactly. You need images that encapsulate the essentials of felinity. You might need humans to sort through and label the data by hand, or if it's already been labeled, checking them against ground truth or unintended biases. Once you have well-curated and prepared data, you split it up for use in training, testing, and validation. It might require a ton of work to collect and label that much data, but it may be worth it. If your data is too sloppy, homogeneous, or scarce, your results could fall apart in the real world.
But also beware of overfitting, in which your model conforms so tightly to the idiosyncrasies of your training data it can no longer generalize enough for the real world. But so long as you have the right data and enough of it, you can...
Hold on, where did she go?
Ooh, does that door lead to what I think it leads to?
Human, wait! Be careful up there!
Come on, we all know where this is heading. It's machine learning's biggest sensation nowadays, neural networks.
Yes, it's true, and yes, a lot of the examples we gave can only be done with neural nets.
But taking them on is a big step.
Grr, it's locked.
Artificial neural networks are powerful tools, but they can eat up time and money.
Depending on the task, you might not need one. Want to sort messages, for example? A naive Bayes classifier is super fast and much cheaper than most neural nets.
Gotta make hiring choices? A lot of people still use decision trees. Easy to understand, easy to review. And support vector machines are powerful classifiers.
Who doesn't love a wide margin?
But I still want to learn about neural networks because they...
Because they're cool?
Yeah, because they're cool.
They are pretty cool.
You know what? Maybe I will will need a neural network, and maybe I won't, but there's only one way to be sure. I'm ready to go through this door and face the future. Now, let's have that key.
You know we were always going to give you the key, right?
Perfect. Well, yeah, this would be a really weird comic if you didn't.
Cue last panel. Next stop, neural networks.